So here we are going to talk about analysis tool development for lower Earth orbit communication for satellite constellation. So in order to understand any satellite communication based problem, we need to have basics of two basic laws, that is the Newtonian law and the Kepler's orbital law. So the Newtonian law states that F is equal to G m1 m2 upon r square, which is the basis for the two-body propagator and which is later used in this project. Also, I need to reinstate the Kepler's law here, that there are three Kepler's law which is very foundation of this project. The first is that the planet move in a plane to orbit described are ellipse with the sun at one focus. The vector from the one sun to planet sweeps the equal area in equal amount of time. And third is that the ratio of the square period of t of revolution of planet around the sun to the cube of the semi-major axis of the ellipse is the same for all planets. Considering this, there are the 6 Keplerian parameters which are very important to calculate the orbital ground track. The first is the semi-major axis. It is the half of the sum of a perigee and apogee distance, and it is usually measured in kilometers. Second is eccentricity. It describes the how ellipse is elongated and how it is shaped is. For example, for circular orbit, the eccentricity is equal to 0. Next is the true anomaly. So true anomaly is the angle between the perigee and the satellite orbital plane at specific amount of time. Fourth is the inclination angle. So inclination angle is the angle between orbital and equatorial plane. The right ascension node, or we can say it as RAN, is the angle between the reference direction and the ascending node, which is the plane where the satellite crosses the equator while going from southern hemisphere to the northern hemisphere. And the last is the argument of perigee. So argument of perigee is the angle measured between the ascending node, that is RAN, and the perigee. After getting the idea of these 6 orbital elements given by Kepler, we will be heading towards making the ground tracks. So in order to understand what is the importance of a ground track in getting the link budget of the satellite constellation, we need to understand the importance of the inclination angle. So the inclination angle is a very basis of any orbital ground track problem. For example, in this case, we have calculated multiple ground track, and by changing its inclination angle, so we can see the difference in the area of coverage. So here in this part we are going to talk about the simulation part of the constellation design, and following that we will be going towards the calculation of a link budget through the parameters that we are getting from the latitude and longitude of the constellation orbital track. Here we have kept the value as the user defined, so that user can input their values and get the desired output. So we are trying to make this model as a user friendly more on the side. Let me first delete the existing value, so that we can see that how by entering the value we can get the specific type of output. Just a minute. So here, as you can see, that now we don't have any value that we are able to see. Now we have entered the specific value, that is a latitude, altitude, that is 400 degree, semi-major axis is given, eccentricity, argument of perigee, inclination angle, and that is all being user defined, so that we can enter it one by one and can get output. It was previously 45 degree, so let me change this value to the 60 degree, so that we can see that how it affects the output. Rest is the thing about the RAN. It is the right ascension node. It is being taken from the SSC filings of the satellite data. Now these three things, the phasing angle, the number of plane, and the number of satellites are the most important part, which we haven't discussed in the previous thing, because it is related to the constellation.
So here we have kept the phase angle. The phase angle is is a difference between the difference between the planes. So what is if the one satellite is rotating in this plane, the other satellite should be rotating in certain distance so that they cannot collide. As we are talking about this, there are thousands of satellites in this sky which are revolving, so we have to maintain the phasing angle so that there is no interference, or we can try to avoid the interference that is being existing over this place. Following that, there is the number of plane and number of satellite mean anomaly is given. The simulation time is that we have taken the time for which the satellite or the orbital track will be calculating its value. So it can be 1 day, 2 day. It is upon the user which is being defined. Now I will be just a minute. I have kept the orbital period as 2 so that we can change the number of times of orbit that we want to visualize. We have so that by entering this, I have entered 5 so that we can get the 5 times that the orbit is being rotated. As you can see that the time value is being changed automatically as it takes the value from the input parameters. And through this, the XYZ coordinate, the ECI vectors, the RAN is being calculated from this, and by taking those values, the latitude and the longitude coordinates is being calculated. I have covered this in the report and the PPT part so that we can refer the calculations and we can refer the equations through which we are getting the values of the latitude and the longitude. Now heading towards the next part, I want to show you that what was the logic that has been used behind calculating this orbital ground track. So I have created the Visual Basic code so that we can make this model very accessible, and by running it in a single button we can get the values so that we can visualize the orbital ground track. So this is a code for the Excel. We can see that we have entered and we have coded in such a way that it takes the value from the orbital parameters that are being user defined. Now this is the code that is being used to get the values in such a way that we are able to design the constellation in the Walker form. Here it is being calculating the RAN for the individual constellation and RAN for the individual constellation, and it is being further used to calculate the X, Y and Z coordinate, which can be used for calculating the individual latitude and longitude coordinates of the satellite. So now as we are in the home page, we just need to click on the run simulation button. So as you can see that the values are all being automatically calculated. The RAN, the XYZ coordinate, the latitude longitude coordinates are being calculated, and it is for the 2 satellite revolving on the 2 plane. So 1 satellite per each plane. Now the RAN, we can see that these values are being authentic as it is being calculated by the conventional formula. So it will be easy for us to visualize this through the maps that are being built inside this Excel, so that it can be easy for us to check the area of coverage, the 3D visualization of the Earth, that how a certain satellite configuration can satisfy the need for the communication. So this, so as you can see that this, I have set this value earlier for the 45 degree. You can see the area of coverage and the 3D view that can be affected by changing the inclination angle. But now we have changed this inclination angle for the 60 degree. So now by refreshing the data, we will be able to check that what is being changing by getting the value, by getting the model to be work. As we are refreshing the data, we can see that there are 5 orbits as we have put in the into the user defined form, and the color of the orbit is being signifying that there are 2 different satellites in the 2 plane. So these 2 satellites are being rotating and are able to cover the part of the Americas, and it will able to. So this point that we are getting, it's being used by the link budget part, and we are entering this value. We have program it in the such way that it enters this value into the satellite latitude and longitude, and it enters the value that we can see in this row one by one, and by clicking this button, it will automatically take this value and will help that to calculate the link margin and the other parameters, the signal to noise ratio and all. So as you can see that the latitude and longitude is an important parameter for calculating the earth distance, the distance, link distance. Then from link distance we are getting the value of atmospheric loss, free space path loss. The EIRP is also being calculated from this. The noise figure and the noise temperature is also being calculated from this. After that we are getting the C by N naught, the signal to noise ratio for both uplink and downlink, and after that we are getting the cumulative or the total signal to noise ratio and the link margin. By this we are able to get from this constellation model, we are able to get the visualization for the link budget, or the signal to noise ratio versus link distance, and the link margin versus link distance. So as you can see that it is the previous one, so I need to update. So as I click on the this calculate distance, we can see that okay, so just a minute. Before getting towards this, I want to show the logic behind this. So how it is being calculated. So you can see that this is the code that we have used, so that it can take automatically value from the Excel sheet and can get the value from the link and the constellation part. So as I have refreshed this, we are able to check that. As we are able to see that as the link distance gets increases, the link margin and the signal to noise ratio decreases, and it is being very obvious result, because it is being difficult for any signal to travel at the long distance without affecting it by the losses that are present in the atmosphere.